Hello, I am glad to proceed Doosan Robotics Core Plus training for our business partners. My name is Yong-hee Han. Today, I'd like to talk about the Smart Vision module SVM. During the training, if you have any question, please write your question on the chat window. Then you'll get an answer after training. Okay, let me start. This training consists of 9 parts. First, we are going to learn about vision overview. This slide shows robot vision overview. Robot vision can operate the robot by processing visual information that use a combination of camera hardware and computer algorithm. In general, vision technology includes computer vision algorithm, machine learning, and parts of motion vision. In case of robot vision, purpose is that it provides the environment and the motion information such as transformation matrix or coordinate relation. Robot vision is implemented using a 2D or 3D camera. It includes a calibration procedure to correct the position with the robot. And it is possible to recognize the detect object to perform robot tasks. In addition, robot vision can provide creating or modifying the robot's path in the field of visual surveying and collision avoidance area. Available applications are various. Object detection is a well-known application, and it can adjust robot pose and posture using Landmark. Also, it can detect barcode or QR codes and measure objects such as diameter, radius, and angle. Doosan Robotics developed a robot vision system. The name is Smart Vision Module called SVM. SVM has a camera, processor, and storage like a mini PC, so vision task program is needed. Doosan Robotics provides vision task setting program and vision task execute program respectively. The vision task can be set up through that platform or that vision. In order to play the vision task, it can be used by that platform or that studio. SVM main functions are here. There are object recognition, presence check, measurement the circle, and measurement the line, and measurement the angle. It provides calibration functions, but convenient calibration function will be described later. After version 2.8, we support new functions. There are hand-eye calibration and auto-calibration. It is possible to use in that vision. In previous version of calibration, there was a possibility of human error because additional tools were required to be installed. However, in the current version, it can be calibrated by teaching directly without additional tools. And auto calibration is used by adding automatic lava motion. In detection aspect, as you know, SVM is 2D vision, but SVM provides a solution that enables posture estimation for 3D by using Landmark. And also barcode QR code detection function has been added. This slide shows the vision solution provided by Doosan Robotics. It can configure various applications by using SVM or third-party vision. The interface could be configured by using Doosan Robotics language DRL. This is procedure that should be performed for the robot vision application. In general, vision system must establish a setting called teaching in advance. Based on the set value, it may be played through a combination with the robot. The following example shows the contents of teaching and play. In order to set up and execute the vision task in SVM, the following program supports. That platform and that vision are used in teaching, and that platform and that studio are used in play. When using our third-party vision, teaching requires a third-party setting program, and it can play using a dot studio. In this chapter, we are going to learn about dot vision. Dot vision is software that has been applied since the launch of v2.8 and is a program that allows SVM to set jobs and test. Operating system is Windows 10 and 64 bits. The screen consists of 4 tabs. If you run that vision, it will be located on the System tab as the same current screen. Let me tell you about the System tab component. It consists of total of 5 panels, and it is a SVM connection panel located at the top, and this part includes component for IP input and connect, disconnect, and IP search. Please note that when searching the IP, you should try to search while Wi-Fi off status. Below is a right view panel. It is displayed on the screen a real-time image transmitted from SVM. It is a function that can capture real-time image on the left. There is a right capture view panel. When clicking on capture, the currently streamed video is captured and displayed, and the photo is stored in the .vision folder in the C drive. A camera setting panel can adjust and store various parameters of SVM camera brightness, focus, and exposure. There are up to 5 storage units, and U1 can be deleted and created as needed. It also has an autofocus function. The software information panel displays SVM version information and serial number on the screen. This slide is for the calibration tab component. It consists of a total of 5 panels. The upper left is a live view panel. Real-time images are displayed on the screen, and 2 buttons of live on and shoot can be used in toggle type. A calibration status panel allows you to check whether the calibration completion status and registration complete in the SVM. And this is robot connection panel to receive robot posture information in upper right corner. There are robot input, robot IP input, connect and disconnect, and access control and servo motor activation buttons on the robot. You can check each status with a checkbox mark. The hand-eye calibration setting panel has 5 input boxes of data. The shoot post panel can set the height of shoot position after calibration completion. This slide for the Vision Tab tab component. The Vision Tab panel at the top left register the Vision Tab creation and deletion image and sets of ROI. The bottom left, the coordinate status panel can select a pixel coordinate system of the camera or robot coordinate system using millimeter and angle. You can use zoom in and zoom out on the right, and the mask setting panel sets a masking area on the image display on the Vision Tab to activate the area and minimize the influence from unnecessary paths by black and white processing. And the detection setting panel sets a similarity, rotation range, and accuracy level when detecting Vision Tab. And the recognition setting panel is component necessary for image processing, post-processing control. After registration, registered image can adjust the edge threshold, low, and reduce noise. And there is a button to apply the parameter set in the upper right corner. This slide is for the detection tag component. If it consists of 4, there is no vision tool work. only two left slices exist. The upper left is object detection panel, which is a component necessary for vision job detection, and below information on vision job is shown. The upper right is a component necessary for vision tool work, and the lower part consists of a panel that displays information corresponding to the tool. In this chapter 3, we are going to learn about SVM function practice. It is summary of SVM terminology. Terminology used in SVM can be divided into two. First is object and second is element. In the case of an object, it refers to an object and user setting area to be searched in the entire range of the camera view, and a change in the position of object and user setting area can be recognized. There is an example of the object on the right. An element is search based on detailed area that need to be searched within the set object or relative location within the object area. And there are feature, edge, circle, and so on. If you catch a large ROI and use it as an object, you can catch a small area of the feature or line as an element, or a circle itself as an element. An object is a higher concept of the element. And I will explain function classifications. It is divided into two functions: work location calibration function and inspection function. In case of work location calibration, it is divided into object detection and element detection, and inspection is divided into presence inspection and measure inspection. Object detection search for an object corresponding to an area set as a function for object detection in the entire range of camera view to find location. As in the example, when an object to be recognized is set and an object is detected for path, location information could be known. And element detection is a function of recognizing detailed the element within a recognized object. And if you look at the whole as an object, you create an element feature of a small component and find a relative position. And presence inspection check the information on how much the component intensity is included through a binary image based on a histogram to check whether it is pass or fail. measure inspection, measure the geometry relationship between edge circle set in the recognized object. It has the function of measuring the distance between the two edges, radius, diameter, or each circle's shape. Object detection, object and elements are used in SVM through one matching between vision job and vision tool. The use of object detection is essential. It can set element measurement inspection in set object. Object to perform an object detection is defined as a basic unit called vision job. Each element in vision job is defined as a basic unit called vision tool. You can create objects and make them into row or hierarchy of various features. Feature 1 can use presence inspection, and circle 1 is subdivided into a measure inspection and can proceed with the work at the same time. In the case of entire object, location information may be returned through object detection. Object recognition and location detection function. To practice the function, we use .vision program. First, SVM correcting on system tab and create vision job, and register image and RY of image registered object is set, and define for the object to be recognized. The picture below is an example of object detection. First, the SVM correction is corrected after entering an IP address, and after moving the third vision tab, click plus to receive an identification number of the vision job 1000. Click the registration for the image registration. After taking a snapshot of the streaming video, there is a screen showing the contour of the edge. Among them, array of the object is selected to define which object to be detected. Click on Set Array button and drag it. The process of object recognition is finished. When you click the detection on the upper right side of the vision detection tab, you can see that a coordinate system is created in the RY of the object, and you can see how much rotation of location information for the object. It is part of teaching. And then you will find out through the video. When the recognition process is complete, it is activated in green on the job list. If you change the list after configuring various jobs, you can check the component information when the detection is performed. Next is set and detection of presence inspection. The normal value can be checked by the amount of intensity of the histogram based in the original image, as shown in the table on the right. You can see the pass or fail. The method of setting the ROI of an object is the same as the other object recognition and location detection previously. After setting the ROI and create vision tool, click on set ROI and drag which part to check the presence or absence. Click the histogram button and set the area. The horizontal side shows the intensity level, and as it goes to 0, it becomes closer to white, and it goes to 255, it becomes closer to black. The detection range of good product may be determined by setting the pixel range. When the object detection is pressed, even the vision tool is automatically detected. Information can be checked by selecting presence from the tool list. When the inspection value is 1, it means that it is located within the set range. Okay, next, I will explain set and detection of geometric measurement. Detecting angle and diameter is no different from detecting distance. So I'll explain it is based on distance. And connecting SVM on system tab and create an object are the same as before, and select a distance label. Afterwards, create vision tool and identification number is generated. We need to set up 2 ROIs. After setting the first and second lines, the corresponding edge portion is detected and recognized by dragging. After checking the distance relationship between the two, the range for the normal value for the displayed measurement distance is set. If you click on the set button, green is activated. Afterwards, if you click object detection on the detection tab and click distance on the tool list, inspection 1 is located within the normal value set range as shown in the picture, and if it is another value, it is outside the set range. In chapter 4, I'm going to explain a newly added function, calibration. Vision calibration is a process for matching the coordinate of the camera with the coordinates of a robot. Since the camera has a coordinate system expressed in a pixel, and the robot uses a task coordinate system, so it is to match the relationship between two. Estimate the camera matrix and the relationship between the camera and the robot. If I explain it as a pinhole camera model, as shown in the picture below, it is expressed as a extrinsic parameter from the camera lens to the physical space of the object. The distance refracted into the lens inside the camera and settled in a material such as CMOS is set as our intrinsic parameter. Use the matrix formula below. It also includes the relationship between the robot's task coordinate and the camera's position. Prepare our calibration board and install the SVM on the robot according to the installation manual. Calibration can be prepared using the data vision program. Calibration can estimate the relationship between the SVM corresponding to the eye and the flange corresponding to the arm. Flange. So data vision support hand-eye calibration and auto calibration. First, we are going to learn about hand-eye calibration. Connecting to the robot in robot connection panel and access on control and operate the robot throw server on. Teaching directory so that SVM can shoot the calibration board. SVM should be positioned so that the calibration board can be fully visible. Click the Save button and the image is saved along with the task coordinate. And repeat for 5 different lava poses and save the posture by clicking Set. And calibration calculations are performed based on obtained data by pressing Run button. The photographing posture height can be set in the Shift Pose panel. 300 mm is the default value. The value can be set between 300 and 600 mm. The setting height is vertical from the calibration center to the camera lens. If you click Move after setting the height, the robot will move to that position. Press and after press registration to register calibration information in SVM. It is a demonstration video. And connecting with the SVM and connecting with the robot. And manual guide and capture pose using the set button. It is important to make 5 different lava poses. It depends on the calibration accuracy. And rest 5 fifths pose set and run and set height, move, and last register button click. And next we are going to run about auto calibration. Automotion is added to the hand-eye calibration function. Collect data by performing pivot movement based on the initial posture. Auto calibration obtains data for 20 different postures. The user only needs to provide one posture, just one. The order from 1 to 3 is the same as the hand-eye calibration and set only one initial posture. And then motion check is optional function based on the current posture. It is a function that checks in advance if 20 pivot motion have enough workspace or singularity problem. When you click the run button, it will perform a calibration calculation after each pivot posture. The photographing posture height can be set in the shipper's panel. Press registration to register calibration information in the SVM. It is auto calibration video, similar to the hand-eye calibration procedure. If you need, autofocus is needed. Set the initial pose and motion check. This procedure is optional. and then calibration 1. As you can see, this is a pivot anchor, and set the height and move. This is shift pose, and then finally click the registration button. This is caution on calibration. Position of calibration board must not be changed while performing calibration and until press the registration. The user directly use instruction or jog to make 5 different robot posture, including orientation. This is important. In robot posture created by the user, calibration board must show all checkboxes in the screen without any cutoff or distortion. And an important part is that calibration should proceed without robot TCP setting. If TCP is set, other task coordinate can be retrieved. In chapter 5, we are going to learn about SVM Landmark. I will explain landmark. It refers to a method of obtaining information on an actual 3D space from an image projected onto a camera using feature points of predefined shape. Although SVM estimates only two-dimensional projected image using a 2D camera, we can use a marker to obtain information on three-dimensional pose as follows. It can obtain information about left to right and up and down through the shape, and 3D posture information can be extracted through the homography transformation process. The camera obtains a trapezoidal image through the difference between the image plane and the Markov plane slope, as you can see. If we know the physical distribution of these points in advance, we can know the depth and tilting of the obtained trapezoidal image deformation through the homography transformation. SVM is a 2D camera, but it is a technique to get 3D information. We need 5 centimeters landmark. SVM must be installed on the robot, and the calibration process must be complete through the data vision. And access the landmark detection tab. From the detection tab, the fourth tab of the data vision. From the third tab to the creation of vision jobs, you can proceed in the same way as before. The reason for creating vision job is that when using actual task and DRL, position information can be obtained using the vision job. So you must click on apply button to transform into a robot coordinate system, not an image coordinate system. On the first detection tab, select the second landmark detection and select the vision job created earlier. A screen that automatically tracks the landmark on the right side is activated. If there is a landmark on the screen, information on where it is currently based on the robot coordinate system along with the 3D coordinate system will be updated in real time. When the detection is pressed after tracking off, the screen is updated at every point in time, and when tracking on is pressed, the screen is updated at 1 second intervals. There are 3 options for landmark function. If the offset function arbitrarily gives x, y rotation information based on the landmark origin, the location is displayed on the screen with the robot coordinate system. In the example below, if you want to detect a specific object based on a marker, give the x direction is plus 100 and y direction is minus 30 and rotation is a positive 45-degree offset based on our marker. The current robot base position value can be updated accordingly. Second option is you can choose 3 degrees of freedom or 6 degrees of freedom mode, 6 DOF and 3 DOF mode. In the 6 degree of freedom mode, 6 DOF mode, you can change the Euler rotation. Doosan Robotics usually use a GYG system, but if you need XYZ when applying other application, you can select it. And this is a landmark video. In chapter 6, we are going to learn about SVM barcode and QR code functions. Barcode and QR code detection functions have been newly added. In the case of 1D barcode type, it can be identified in 13 types and supports more than 86% of industry or service area. It can be covered unless it is a special purpose type. In case of 2D, QR code and 2D data matrix can be supported. The minimum size is shown in the following table, so please refer to it. This is a preparation for detecting a barcode or QR code. You need to prepare a barcode or QR code, and SVM must be installed on the robot and data vision program. After run the data vision and connecting SVM on the system tab and select the barcode detection tab on the force detection tab. When the detection is executed, information is displayed on the screen. And optionally, barcode QR code information can be registered in the SVM database and used for classification or comparison based on the registered information later. Click on the registration button on the bottom right to save it with identification number in SVM database. The order is given an identification number as 1, 2, and 3. It can be deleted individually or entirely. This is barcode and QR code option video. Click the detection and then you can see the barcode QR code information on the screen. In this chapter 7, we are going to learn about SVM execution based on the task. In order to execute SVM based on task, we can use a program called Task Builder in Teachpendant or data platform. Prior to version 2.8, we can use vision command in the task builder. But after version 2.8, we can perform the new SVM skill made by App Builder. In this case, SVM skill can be used after installing the file of the DRL extension. This SVM skill offers 3 main types of skill: shoot pose, and marker, and landmark. Of course, you can also use vision command that you used before 2.8. As a preliminary preparation, SVM must be installed in Lava, and Lava must be updated to a version of v2.8 or higher. Afterwards, proceed with the DRL file in the workcell item skill install and install tab at the bottom of the setting in the Teachpendant. After click on install, you can select the DRL file and install SVM skill through USB. This is shoot pose skill. This skill uses data vision to bring up the robot's shooting posture stored with the vision job identification number set. If the shoot pose of the corresponding jump number is set in data vision, it is function that bring the posture of the corresponding shoot pose to the joint posture. In order to use it in task, Robot posture brought in must be stored as a system variable. You can save it as the following system variable's name. Later, stored system variable can move robot with the move_j command. If you look at the task builder screen, there's a support skill. You need to set the information on the support skill in the property tab. Enter the SVM IP address and enter the identification number of the vision job you want to import in the below box. You create a system variable as described earlier. The type of variable is pose. Since the name of the system variable is written in advance, fill in the name of variable called SVM pose. Select the join coordinate system. Call a pose with the get pose button and press add to save the variable. Press a button called suppose check to check if the value of a system variable is updated. When you press the button, pop-up appear one by one. The first message shows pose J value of the suppose. When you press OK, a pop-up for update completion appears. Press OK again. You can see the result value is displayed as success. Next is Landmark skill. This skill uses data vision to bring the landmark pose information captured with vision job identification number that set landmark detection. Landmark posture information is stored in the variable of pose X because it uses the task coordinate system. For use in task, landmark pose information must be stored as a system variable. The system variable must be stored under the name system SVM Landmark as shown below. After that, you can use this stored system variable with move L to move robot. After adding landmark skill on the task builder screen, enter the SVM's IP address and job ID in the same way as supposed earlier in the property tab. And in the optional information column, write down the value to set the offset of landmark. Choose whether to GYG or XYG rotation, the orientation type of landmark to be printed. And create a system variable. The variable name is system SVM Landmark, and select pose type and task coordinate system. Set the initial value with get pose and click the add button. Afterwards, when you enter the property and press the landmark detection button, the pop-up window appears one by one. If the landmark is on SVM camera, the coordinate value of the landmark is shown. When you press the OK button, a pop-up appears that SVM landmark system variable has been updated. Press the OK button again. You can see that the result value changes from right to success. Lastly, the barcode skill. Barcode skill performs the task of calling information on the currently captured barcode. The skill can compare with barcode information registered in SVM database using data vision. For use in task, you need to save the barcode information as a system variable. You should save it as a variable type and save the variable name as system SVM barcode data. The result of comparison with barcode information registered in the SVM database must be stored as a system variable for use in task. Likewise, you should save it as a variable type, and the variable name must be saved as system SVM barcode comparison. Stored system variable can be used with if command. If you add a barcode skill on the task builder screen, it will be configured as shown on the left, and go to property and enter only vision IP address, because barcode skill does not require vision number. Barcode skill requires two system variables. One is a variable that can read the current barcode information called system SVM barcode data, and the other is called system variable barcode comparison that can check the comparison result or whether the captured information matches the value in the current SVM base. After that, you can press the barcode detection button, and you can see that the pop-up appear one by one. Initially, detection information, type, and data information appear. The data information is stored in the system variable and system barcode data described earlier. And if the comparison result is 1, it matches the information in the SVM database. Finally, you can see the SVM has a message window indicating that the system variable has been updated and already changed to the success. In this chapter 8, we are going to learn about SVM execution based on the DRL script. To execute SVM based on the DRL, it is necessary to check the newly added DRL command. Two types of landmark and 3 types of barcodes have been added. In addition, it would be good to refer to programming manual for additional DRL commands for using SVM. You can create and execute DRL commands using .studio or custom code in Task Builder in the data platform. First, the added function. I'm going to tell you about the SVM detect landmark. This function is used to detect landmark pose information based on the camera coordinate using vision job ID. Here, job ID enter the input variable and the data type is integer. If a new vision job created by data vision, the identification number will be automatically given, which will increase by 1000, 2000, and so on. And the output variable is count and cpose. Count means the number of the detected landmark, and cpose is the landmark pose based on the camera coordinate. It consists of 3 translation term and 3 rotation term, and the coordinates are landmark pose information based on the camera coordinate, so you cannot use the move command right away. After going through the transformation work that will be described later, you can use move L command in the task coordinate. If the landmark detection fails, output is 0 and an empty list. Please look at the example code below. SVM connect and disconnect are commands used to connect or disconnect SVM. Please refer to program manual for more details. And when you put the vision job number equivalent to 1000 in the SVM detect landmark described in this chapter, you get the variable in count and cpose. This is an example code that check this value with a pop-up command. The second command is called SVM get marker offset pose. The function calculates the landmark pose of the camera coordinate as a robot coordinate using offset on the landmark. So you can get the camera coordinate through SVM detect landmark used before. The move L command can be used together with using the output that comes out as an output. The input variable is cpose. The offset function performs the same function as the landmark option of data vision described earlier. And translation and rotation can be set to 0, 0, 0 based on the origin, and the value entering the Boolean type to enter the Euler mode is determined by the GYG notation used by Doosan Robotics if true. In the case of false, the value is output as XYZ notation. The output variable is output. If output fails or there is no cpose, -1 is set to be output. This is the example file. The offset value means that 3 translation X, translation Y, and rotation Z value can be applied in the form of a list. If the Euler mode is a Boolean type true value, it means that we will print it out as a GYG. Afterwards, you can put the corresponding input variable in the SVM get marker offset pose and receive R pose as an output value. In this example, you can check the value corresponding to the R pose with a TP pop-up. In actual application, you can enter R pose into the move L command and use it. The next 3 functions to run are commands for barcode. The first is function called SVM get detection barcode. This function can be used to detect information on the barcode or QR code located in the screen. Input variables are not required. When the corresponding function is entered, the variable output must be return 1 to mean the detection success. The output value called B-type is a string of data types and displays the type of detected barcode or QR code. And B-data, which means barcode data, is a string type and displays the information contained in the detected barcode or QR code. If detection fails, 0 and an empty list are output. You can test it through the example below. The second barcode function is a function called SVM get barcode DB data. The function receives index value as input variable. The information is returned to the barcode or QR code registered in SVM database using the index. Registering barcode information in SVM database through an optional button called registration from .vision create an identification number. When you put the identification number in the index, it is a command that returns what the data of the index is. It can be used to check if the information is registered in the database when detecting the barcode or QR code from an actual application. This is SVM compare barcode DB data function. The function puts DB data as an input value. DB data is a type of string and is a function that compares whether the entered information is registered in SVM database. When 0 comes out as an output variable, the information entered is not registered in SVM database. When 1 comes out, you can see that it is registered in SVM database. It can be used to compare whether the actual measured data is in SVM database. In this chapter, we'll learn how to use SVM through example file. The first example program is that implements SVM using Landmark. In the scenario, as you can see on the screen, prepare the jig with the attached landmark first and change the position of jig. When the jig location changes, it is a scenario in which the robot moves to the third point according to the landmark location and repeats the pick and place operation. This is scenario requirements. A landmark should be attached to the jig for pick and place work. The attached landmark should not shake or move. In other words, it is possible only when it is perfectly fixed to the jig, and it requires precondition that it does not do relative move to the jig, and it needs to calculate jig's current pose using landmark detection. The teaching peak pose from the current pose must be calculated. As requirement for robot, needs a shift position to detect landmark with SVM and be able to pick pose and place pose calculated by SVM. You can see the flow chart for this scenario. Change the jig position manually and then move the posture of the robot to the landmark shift pose. After detecting the landmark through the SVM, calculate the value of the grasp pose and instruct the robot to move to the pose information. Lastly, this is flow chart where you give order to the robot about the release pose. I show you our demonstration video. As you can see, change the position of the jig. The changed location was calculated from the landmark. Robot operates a pick and place work according to the position. Although SVM is a 2D camera, it has an advantage of being able to correct the location of 3D pose changes using landmark. And it would be good to understand it as an example program that utilizes the advantages. It is responding not only to rotation change in the plane, but also to change in three-dimensional tilting, position, and depth. The following example is that use AMR and SVM in more complex. In the scenario, as shown in figure below, instruct the robot to object to be picked and move it to the pick position using AMR, and then identify the object, the SVM. Pick up the instructed object and AMR move to the place position. Afterwards, it will be an example of recognizing the box placed for each object through QR code and put it down on the correct box. This is a scenario requirement. In AMR, it should be able to move the location to pick and place, and SVM should be able to detect 3 different objects and correct the position error using landmark. And also SVM should detect QR code and compare the detected information. And the requirements for robot need a shift pose to perform object detection and pick position, and a fixed posture when moving the AMR, and shift position to detect landmark and QR codes, and need to be able to pose the object. You can see the flow chart for this scenario. After starting the program, when the robot is instructed on object that need to be picked up among 3 objects, and then AMR move to the pick place, and when the movement is complete, the robot take a shift pose and check the object given the command in shift pose and pick it up with object detection after checking. When the process of picking up the object is complete, AMR will move to the place location and then take a landmark detection shift pose to detect the landmark. Using the landmark position correct value, robot can get posture information to shoot the QR code and take a picture of QR code to check if it is the correct box of the object which is initially instructed, and if it is correct box, robot will put the object down. Let's take a look at the example video of the SVM demonstration with AMR.